Okay, so in this video we're going to be talking about the colors and especially the visible light colors that and how they interact with us and how we see things. And it's pretty simple actually, and we're going to be talking mostly about 28.2 color by reflection is the most important. But first we're going to do a quick little review of the electromagnetic spectrum because it's important that you know that. So electromagnetic spectrum goes like this. Very simple. I remember or I'm sure you guys learned it in chapter 27, which is all about light. But we're going to talk right now radio waves, microwaves. I'm not going to write the waves, it takes too long. Infrared, visible light, ultraviolet, and ultraviolet X-rays. Sorry, I get caught up a little bit. It's not an easy thing to remember. And gamma rays. Now, I did memorize this, and I have a kind of a way for people to memorize it. I don't know where I learned this. I think I learned it back in middle school, but I use real men in Vegas use X games. I don't really know what it means, but I memorized it, and that's how I know it. Now, what we're going to be talking about in chapter 28, which is all about color, we're going to be talking about this right here, the visible spectrum. Now, the visible spectrum actually encompasses a lot of things. That's what we're going to be talking about in this section. Um, so what we're going to be talking about is visible spectrum. Spectrum. And basically, in terms of wavelength, the human eye can pick up about from 390 to, let me think, 750, I believe, nanometers, which is very small, mind you, um, nanometers. But that means that we can pick up colors in the classic color wheel, red, orange. I can't believe I'm not doing these in the color in their respective colors. Um, red, orange, yellow, green, blue, and finally purple. It's not really purple, it's more of a purple. Oops. A little bit of lag time there. Purple. Okay. Red, orange, yellow, green, blue, purple. Roy G. Biv, I guess. I guess some people like to add in, um, instead of purple, they do indigo violet. Indigo violet, right? So whatever you want to do, purple kind of encompasses indigo and violet. I don't mind either way. I mean, of course, why should I care? But yes, that's how I do it. And we can see all of those colors, but the question is, and it's kind of a philosophical question, but scientifically we can explain it using physics and resonance and atoms and all that fun stuff. But the question is, why are things the color that they are? Why is the computer I'm staring at right now, a combination of black and silver and white? Why is this page on the book, why does it have white and black and green? And then, why do things have the color that they have, and how are these mixtures represented to our eyes, and why do we pick them up that way? So I'm gonna refresh this page, and we're gonna look at answering that question. And to start answering that question, we have to look at section 28.2, color by reflection. And reflection, along with transmission, is the main way by which things get their color. Everything has a color. Hold black, which is the absence of all color, but we'll get into that. But I'm looking at my wall. It's painted like an off-white. Why is that? And we're gonna look at this term, reflection, when things bounce back. So the example I like to look at is, let's say I have this backboard. I don't think we Maybe we have them at Priory up in the middle school area, and but I'm not sure up by Church Square. But you have this backboard that you play with at recess, and you have this ball and you throw it. I throw the ball here and it kind of bounces and then it hits here and it bounces back to me, bounces back. Remember Newton's laws? So it goes here and it goes back to me. It reflects off the wall essentially. It bounces off. We use bounces, but bounces and reflects can be used pretty interchangeably. So now we're going to look at, well, why is this ball red? Why is this wall yellow? Why do things have their color? So, and how does reflection play a role in this? How does this bouncing ball affect colors? And so what you're gonna look at, let's kind of do a zoom in on this ball. Okay, this ball is red, as you can see, and it's red because it has atoms inside of it. Believe it or not, let's take a little cross section of this ball. Inside this ball, there are little tiny atoms, right? These little building blocks. Building blocks. Here's your nucleus, and I'm just gonna draw a nucleus and an energy ring. Nucleus, energy ring, nucleus, energy ring. They're super packed tightly, bonding with each other. You'll learn chemistry, and they bond to each other, and they attract, and they break apart to cause energy and stuff like that. But they also move. These little electrons on these energy rings, they're always moving because they're full of energy. They're very excited. They're moving about. They're very energetic. And they're moving at a certain frequency called their natural frequency. And we learn what frequency is. Remember, I'll write it 1 over wavelength. But you're not going to really need that equation now. But it's always the inverse of the wavelength. Because as the crests and troughs occur more frequently like this, that was kind of a bad example, but as they're pretty frequent like that, the wavelength is, rather small, but we're not going to get into that right now. This ball, the atoms in this ball have this certain natural, this resonant frequency, and when you get sunlight coming in from the sun, I'm going to draw it from down low, but obviously it would come from up high, oops, coming in from the sun, colors reflect, and I'm going to go into more detail. But first I'm going to explain, why did I draw the sunlight white? I mean, we all know the sun looks yellow to us, but sunlight is the composition of all the colors, the Roy G. Biv. It's the composition of all that, compilation together into white. So when you combine all those colors, you get white light. And so that's what we're getting from the sun. We're getting white light. And so white light from the sun hits this ball. And inside this white light, packed inside it, you have your reds, your oranges, your yellows, your greens, and your purples. Those are all inside the white light wavelength. And what the atoms do, they're bouncing about, moving about, and they say, okay, well, I'm getting hit with all these different frequencies of light because all the colors have different frequencies at which they move or oscillate back and forth at. And the atoms, being all the same in this ball, they say, let's say this atom over here gets hit with white light. So it gets hit with all those colors, all these colors it gets hit with coming in. Now, the colors, I should have probably drawn that red because we're looking at the red ball. All right. Essentially what happens is this atom, these electrons on the atom are moving about at their natural frequency, and when color that moves at its own natural frequency, when certain colors hit this atom, they resonate. And what happens is the ball's atoms absorb those colors, and the electrons actually step out to another energy level. They get so excited that they bump up to this next energy level because they have so much energy. They bump up because the higher energy levels you go, the more energy you have because the stronger the pull between the nucleus and the electrons. But that's for later. But the electrons get so excited because they resonate with this light. They resonate with the orange, the yellow, the green, the purple, the blue, the purple, right? They resonate with those and they hold them, they absorb them, they take that energy. But then you say, what about the red? Why don't they resonate with the red? The red has too low a frequency for this atom. The red is oscillating at such this elongated transversal. It's like, so slow, right? And the atoms say, I don't like that. I'm gonna spit that out. I don't need that. I don't need that low frequency. It's not enough energy for me. The too big of a wavelength. Oh, it's my dog. If you heard that, but yeah. So what they do is they spit it out. They spit out the red. They don't want the red. So the red gets spit back out. And where does it go? It goes to our eyes. And that's the gist of color by reflection. The light spits back to our eyes when it's not absorbed. And so the last thing I want to talk about is kind of wearing clothes. Now, if you're wearing a shirt that's white, let me just draw. I'll just draw the color white. Okay. You have white here. And white really is, like we said, a composite of all the colors. Right? It has your reds, oranges, yellows, greens, blues, and purples. It's a composite of all of those. And basically, sort of the indigos and violets, sorry. Basically, when you're wearing this white t-shirt, why is the t-shirt white? Well, that's because white light hits the t-shirt from the sun. And like we talked about with the ball, there's atoms in the t-shirt. And those atoms inside the t-shirt are, of course, oscillating at a certain frequency. Let me try to draw an atom again. Here's an atom, right? And all these electrons are oscillating at a certain frequency. And then white light comes and hits it from the sun. And what the atoms in the white shirt do is they say, "Wow, I don't like any of these colors. None of them work for me. None of them resonate with me." So it spits them all back out. All of the colors go right back out. And when all the colors are spit right back out, we're still seeing white because all of the colors are still there. But what if you're wearing a black shirt? So I'll draw the color black for you. Black. It's kind of inside this white circle. Black is the absence of all colors. So let's say white light hits this, let me do a little erase. Oh, that doesn't do so much. Oh, I know what I'll do. Kind of trace over it in black. Okay, so we know that with the white shirt, the white atoms don't resonate with any of the light. They don't resonate with any of these colors, right? None of them. Oops. Doesn't resonate with any of these guys. So what happens is he spits them all out. What about with black? So how about these black atoms? Okay, I'm going to draw them in white again just because for lack of, we have a black background, so I can't really. But when black atoms, or atoms that are in something that's black, are hit with white light, again, light with all the colors, it says, "Wow, I love all of these colors. I love the red, I love the orange, I love the yellow, green, blue, and the purple. They resonate with me on all the frequencies resonate with my atoms. I want to take those in for my energy." And so what it does is it takes it in. All the atoms, they absorb it. And the electrons bump up to the next energy levels. And they're happy now because they have new energy. But what happens is that energy is in the form of heat, so you get really hot. So that's why it's true you should wear white on a hot day because it reflects all the colors. It reflects all that heat. You're not going to get as hot. Whereas a black shirt absorbs everything. So nothing is bounced back to your eyes. Nothing's bounced back to your eyes. No colors are bounced back to you. So you don't see any color, which is black, because all that color is sitting in your shirt in the form of energy. And that's the presentation on 28.2, and it was very, very long. The next video will be hopefully through to 28.5, which is mixing colors, through that, and I'll see you in the next episode.